But I'm delighted to be here and to be speaking at this celebration of Maxime. Well, I've known Maxime for many years, and I remember once we were having some mathematical conversation, and it was pretty complicated, and so I was wondering, well, how did you think of this? How do you know this? And Maxime said, oh, of course, but there's gravity. Remember that? Gravity. And so that was it. And so I've learned a lot of mathematics from Maxime over the years, and it's always very inspirational. And some of my talk will be about ideas maybe from physics and how they are perhaps useful in arithmetic. Anyway, so we're talking about K3 surfaces, and well, algebraic K3 surfaces, giving algebraic equations, and labeled by even positive integers, degree 2 K3s are double covers of P2, ramified and asextic, a quartic in P3, the most famous one perhaps, intersection of three quadrics, or a Kummer surface, blow up of the fixed points on a given surface when you quotient by the involution, x goes to minus x, a Kummer surface. So here is a page from Klein's protocols from 1876. A student of Klein made models of K3 surfaces, Kummer surfaces, and nach den Zeichnungen von Professor Klein. So Klein made the technical drawings for that, and then there is here das Modell here. And Klein himself gave lectures in his own seminar on Kummer surfaces. Here we're reading about Kummer surfaces and the connection to hyperelliptic functions. Perhaps a reference to the abelian surface that we've seen before. Now, so why are we thinking about K3s? Well, first of all, there is fascinating geometry, and usually one talks about Kummer, Kähler, and Kodaira. And people are wondering why K3, and I have an explanation here in 1882. Again, Klein, his own handwriting. Here we see K dot, well, I interpret this as a 3. And then there is another one, K dot something. In any event, there is a reference to Andre Wales that has something to do with some mountains somewhere, but I don't believe that. In any way, there are also interesting connections to, well, string theory, mirror symmetry, mathematical physics. Perhaps our universe has something to do with K3s, I don't know. There are connections to interesting groups, monster groups. And just to begin, just to warm up, so curve counting came up in mirror symmetry. And it's quite fascinating. You write down some generating function with growing coefficients, rapidly growing coefficients. And this is supposed to count rational curves on a K3 surface. This famous formula by Yao Zaslov was established over the years. And that curve count is supposed to be connected with, well, maybe something in the mirror world. And I don't know really about mirrors, but if you have an algebraic K3, which is general, so rank Picard 1, well, then the mirror thing, at least I can read what it is. There is a one-parameter family of dual K3s, which are of the form, one elliptic curve times another by an involution, so a Kummer case. In fact, the quotient of the mirror by some involution is with Kummer case. Now, another interesting thing maybe to note, well, there is something called the elliptic genus, a function of two complex variables, but when you evaluate in 0, you get the Euler characteristic. Well, that's kind of amazing. But then, if you expand this function into something, and you see coefficients showing up, then suddenly these are dimensions of reducible representations of this monster group there. And the subsequent coefficients are sums of such dimensions. Sorry?
Mathieu.
Yeah, yes, okay, Mathieu. Now, I got this paper from Iguchi, Oguri, and Tashikawa as a submission to the Journal of Experimental Mathematics. I'm still one of the editors, and I was really stunned that something like this can happen. And this was established recently by actually several groups of people, independent publications. So it's a theorem. Well, that particular group has something to do with another group, and sort of an algebraic geometry. Mukai established that if you have symplectic automorphisms, then in fact, well, over K3 they are embedded into this M23. Now, so this is all on the sort of geometry side. The main questions for us. We work over non-closed fields, like finite fields, number fields, or function fields of a curve. And the kind of questions that we want to ask are, well, are there rational curves or rational points? And when they are, well, are they dense, maybe in the risky topology or in some other topologies, perhaps potentially dense after finite extensions of the ground field? So, and what I'd like to do today is to survey some ideas and techniques in this area of arithmetic geometry. And some of those techniques are inspired actually by developments in mirror symmetry and some high-dimensional algebraic geometries. All right. So first of all, let's start with simple examples. There is this particular diagonal quartic, and there was a conjecture of Euler's that there are no non-trivial solutions. So trivial would be 0, 0, and 1, 1. And that was disproved by Elkis. He produced infinitely many solutions over the rationals. And then there was another conjecture, more recent, by Surt and Dyer, actually, that this particular diagonal quartic has no non-trivial solutions. And here trivial would be, again, 0, 0, and 1, minus 1, 1, 1. And, well, when it came out, so it was sort of natural to try to disprove it. And my postdocs in Göttingen, graduate students, ran a computer and found that there is actually a non-trivial solution. And here is a solution. And then, well, they had to do a lot of work, because what do? I mean, you can't do approximations. It's really integers. So you have to try integers, from here to there, from, say, minus 100,000 to minus 1 million to plus 1 million, and see what happens. And it takes a lot of time. They had to reprogram basic arithmetic for that. In any event, they found no other solutions up to 100 million in size. So we don't know, are there infinitely many solutions? Are there only these two, or these, the ones obtained by changing signs, and so on? So in other words, the arithmetic of K3s, is hard, even sort of computationally. Now, so what kind of geometric invariance will be relevant? So we have a polarized K3, and well, we have its Picard lattice, and it sits in H2, and so this is what we have, some distinguished lattice. And well, the Picard rank, the Picard group is just z to the rho, and that rho, it can vary from 1 to 20 for fields of characteristic 0, but over fp bar we are not allowed odd numbers, we're only allowed even ones, but we can go up to 22. So this is a basic invariant, and so we have an intersection form on Picard, and we can learn geometric information from looking at this form. For example, if in this lattice, in the Picard lattice, we have a class of square 0, well, then we have an elliptic fibration, and then we can use it to prove something arithmetic. Now, how do we compute this Picard lattice in practice? So, or even that number, even the rank. So for fp bar, we can do this by simply counting points over finite fields, computing the Hasse-Weil zeta function, and we can do brute force. We can just plug in numbers from 0 to p, and in any event, we have to do this computation because H2 has rank 22. We have to go to sort of the middle. In principle, we have to go up to p to the 11. So p to the 11, and if you have let's say 4 variables, so the straightforward brute force algorithm would require p to the 11, and then p to the 33, maybe, or at best maybe. In any event, it's not practical for primes bigger than 10. And in fact, some paper from 2 years ago said, well, for p equals 7, it took 2 days of computer time to compute just that. So, however, there are improvements. You don't have to do brute force. Kedlaya has developed an algorithm, and Antoine Chemerloir explained it in the Bourbaki talk several years ago, how to rapidly compute points. And, well, it is better than what I wrote here. Now, over Q bar, there are some ad hoc methods. If by miracle, if we have a case 3 where in one prime we have rank Picard 2, in the other prime over P2 bar we have rank Picard 2, but the discriminants of those don't match modulo squares, well, then you are forced to have Picard 1 because of these compatibilities of lattices. So sometimes you can just find examples where, what one prime you have is that, and Van Looyk has produced infinitely many examples of K3s of the rationals, quartic K3s with rank Picard 1, geometric rank Picard 1. Now, so Andrew Crash and Brendan Hassett and I, we were thinking about this computability issue for K3s, and we proved there is an algorithm with a priori bounded running time to compute rank Picard and actually all the generators. So, well, and at this stage you can only do it in degree 2. So what's involved? Well, we needed an effective version of Kuga-Satake correspondence. Well, and the other effective versions of techniques in algebraic geometry, effective geometric invariant theory, Masser-Wuestholz effective Tate conjecture, and so on. So, and the main issue, sort of what's the main problem in extending this from degree 2 to other degrees, for example, to quartics, is an effective construction of certain arithmetic quotients, namely quotients of bounded symmetric domains by discrete groups. Well, it is known by a general theorem of Bailey-Borel that these are quasi-projective algebraic varieties. But what we need is, in fact, equations for these varieties, effective equations. Now, there are some instances where this is known. So the Mumford's lectures on theta functions, Mumford does it for moduli of abelian varieties in all dimensions. And we need something similar for moduli of K3s. And degree 2 is very special because in this case it so happens that that corresponding moduli space, well, you can construct it via GIT, and that quotient on the nose is exactly this D mod gamma in this degree. And there are similar things in higher degrees, but they require some further factorizations, and we were not able to push it through. So in other words, we need some effective bound on the generators of rings of automorphic functions, if you like, on degrees of these generators. But given that, we can proceed and bound, compute the Picard rings. Now, compute, again, so what does it mean? As you can imagine, with all the words on the slide, GIT, Kuga-Satake, a K3 surface, gets associated with an abelian variety of dimension 2 to the 19. How do you compute anything on an abelian variety of dimension 2 to the 19? But you see in arithmetic geometry, there are results like this. So in Baker's theorem, for example, in transcendence theory, you have an equation, you have a priori bounds. The bounds are very large, but you plug it into something else, and it's becoming useful later. Okay, so so once we know, let's say we know the Picard group, so we can try to explore some more geometry. What about rational curves? Well, there is a theorem that every projective K3 has at least one rational curve. And, well, very general such surfaces contain infinitely many rational curves. Now, over number fields, well, number fields are countable, and the coefficients and all of this is countable, and very general could exclude all the surfaces defined over your number field. So it would be important in number theory to know that, well, K3s over number fields have curves, many curves. And I mentioned previously that there is a formula that counts curves, or supposed to be curves. But unfortunately, the formula involves coefficients. There is a dn, and those coefficients grow very fast. But the formula does not prove that there are infinitely many curves, unfortunately. And so there are some special K3s for which existence of rational curves can be established directly. And those are elliptic ones, and those with infinite automorphisms. But we have to have Picards of higher rank. For an elliptic one, we have to represent 0, so we have to have rank at least 2. And similarly for automorphisms, we have to have higher rank Picard. In particular, rank Picard 1, you don't know what to do. And in the Kummer case, over a finite field, there is actually the following theorem, which when we found it, was quite striking to us. So if you look at the Kummer surface over a finite field and pick any number of algebraic points, so points over FP bar, that are not on those 16 exceptional curves, then you can find infinitely many geometrically reducible rational curves which are defined over the ground field, over your small finite field, that pass through these points. I mean, this is some kind of version of space-filling curves. So in other words, so you produce many, many rational curves that even pass through prescribed points. So here with this joint theorem with Bogomolov and Brandon Hassett, that again in degree 2, in rank Picard 1, we could prove that the K3, any K3 of degree 2 has infinitely many rational curves. Here I wrote number field. In fact, any field of characteristic 0 would work. So what is involved? Well, in the original argument of, let's say, Mori Mukai, proving that K3s have rational curves, one starts with a special K3 and then tries to move the curves, the rational curves, sort of in a family, and then specialize, and rational curves specialize to rational curves. So that guarantees the existence of some rational curves in the specialization. But unfortunately, in that specialization, of course, many curves could collapse onto one curve, and then you don't know that you have infinitely many. And here, we used sort of a mixed characteristic version of that. Well, we looked at a K3 over a number field, and then we reduced various primes. And the reduction modulo primes was, the special case. We know that in FP bar, rank Picard is at least 2. And in rank Picard 2, we have a chance of finding new rational curves. And then we would try to lift them to characteristic 0. And that idea worked. Sorry. But to sort of control the deformation theory and all that's needed, well, first we needed rational curves, a chain of rational curves. And then, of course, we had to make sure that the sum of those curves, the class, is a multiple of the polarization, the only class that we have at hand in rank Picard 1, so that we're able to lift. And one of the issues we had was transversality and also those intersections. We can't control that. We don't know what the curves are. But if all the coefficients were 1, then we succeeded. And in degree 2, again, by accident, we were able to produce chains of rational curves like this, where all coefficients were 1. So subsequently, Lee and Liedtke proved a much more general theorem that if you have a K3 of odd Picard rank, then there are infinitely many rational curves. And again, they used reduction mod P, but they had another idea, that used, in fact, Kontsevich spaces, rigid stable maps, and, combined with what we did prior to that, they were able to produce infinitely many rational curves. Now, what is the problem? What is left? What's left is rank Picard 2. You see, not every K3 of rank Picard 2 has an elliptic fibration or infinite automorphism. So there are some cases where the problem is still open. And the main issue is, how do we know the rank Picard jumps when we reduce modulo various primes? So there is nothing that guarantees this jumping behavior. If we had that for infinitely many primes, then we could start the previous machine. So let's talk a little bit about the jumping of Picard ranks of K3s. Well, So we already know that if you rank picard 1 and we reduce mod p and look at fp bar, we have to have at least 2. So there is some number here. It only depends on the K3 that you have to add automatically. Well, that function eta, it's, if you have complex multiplication, real multiplication, there is something that you can specify. And jumping would mean that you have strict inequality here. Now, equality does actually happen for infinitely many primes. And in fact, after some finite extension of the ground field, even for density 1 of primes. So the jumping behavior is going to be a rare event. But nevertheless, you want to know, does it happen? Is the set infinite, for example? So, and again, the main concern for us would be rank picard 2. Well, not knowing what to do in rank picard 2, let's look at the Kummer case, where rank picard is at least 17. So the rank picard of a Kummer surface is, well, the 16 exceptional curves that we had. And then, of course, the rank picard of the abelian surface, well, it could be 1. But in fact, if the abelian surface is a product of 2 elliptic curves, well, then you're guaranteed to have at least 18. And if those curves are isogynous, then it's at least 19. Well, and if in addition they have complex multiplication, well, then you're at least 20. And so now we can look at the jumping behavior in this case. All right. So when are we jumping? Well, if you have exogenous curves, then we are jumping if and only if LP is a prime of supersingular reduction, actually. Well, maybe. So, and so does that happen? And the theorem of Elki's from 87 says that there are infinitely many such primes. So there is a recent 2014 theorem of Francois Charles. I mean, I heard his talk in New York just a month ago or so, that even when the curves are not isogynous, the set of jumping primes is infinite. There is no paper yet, but it looked totally convincing. Now, if the abelian surface is absolutely simple, on the other hand, then we don't know. Well, not knowing this, I asked my student at NYU to compute those ranks and compute the jumping behavior. So he implemented this algorithm of Kedlaya that developed for hyperelliptic curves in the case of quartic surfaces that allowed him to go from primes less than 10 to primes less than 100,000, which is significant enough to actually produce some statistically significant data. So what are we seeing here? Well, in the first slide, we're seeing some examples, example 1, example 2, of K3s as geometric Picard number 1. And so we are guaranteed to have 2. But the question is, do we have 4? And we're counting primes up to x and dividing by x log over log x, the number of primes up to x. And this is what we're seeing. Essentially 1 over square root of b. Well, it's not quite square root. It's 4 here and 4 2 maybe here. But, well, those are the data, and that's a line that's supposed to give the square root. Now, if you are in geometric rank Picard 2, on the other hand, in those examples, well, we're supposed to look at primes jumping to 4. And we are seeing the number of those primes. And it's essentially half the primes. Well, it's not really half. Now, you could think that, well, maybe it's complex multiplication or something like this, and maybe field splitting or non-splitting of primes and some quadratic extensions, so half the primes split, half the primes don't split. But it's not the case, actually. And as we can see, there is no oscillation around 1/2. We are going to 1/2 sort of from above. We're not really getting 1/2. So it would be nice to have some heuristic explanation in all cases of what is the asymptotic of jumping primes for K3 surfaces, and would probably involve maybe the Sato-Tate group, some combination of Sato-Tate and Lang-Trotter should give it. So here are some other examples. For example, rank 16, and again you're seeing 0.56 if you like, and here is rank 17, and then we are seeing b to the 4(2) and b to the 4(6). So that's what the computer tells us here. Now, so we understand rational curves and maybe the jumping behavior of primes. Let's think about rational points. And the question is, we have a K3 surface over some non-closed field. Are rational points dense after some finite extension of the ground field? And we looked at the two cases, a number theoretic setup where we're working over the rationals, and also the geometric setup where we're working over a function field of a curve. And so here is sort of the situation that if you have a general pencil of K3 surfaces over P1, then actually rational points are Zariski dense. But here, general really means general, sort of complement to countable subset of things. And so at this stage, we are unable to overcome this. And over number fields, it's sort of the opposite case. If you look at special ones, elliptic K3s or those with infinite automorphisms, then again we have potentially dense sets of rational points. And so let me just very briefly say, what are the problems? So in the first case, we need to know that the jumping primes, if you like, they're not two jumping. We need to ensure that rank Picard is exactly 2 for infinitely many points on the base, for infinitely many primes. 2 and not more. Now, if you again think about the moduli spaces situation, so we have family of K3s, it's like a curve in the moduli space of K3s, an algebraic curve, right, P1. All right? And so what we need to make sure is that this curve does not intersect several Brill-Noether divisors. It's supposed to intersect just one, but not 2 simultaneously. So now when you look at it like this and you pull back the curve before the quotient by gamma, this really looks like some version of André-Oort conjecture maybe, and perhaps techniques developed in connection with that are applicable in this context as well. So we want to say that we're passing through maybe 2 rational subspaces, but not 3 upstairs. So maybe that will work. So this is a problem over a function field. But over a number field, you simply have no ideas how to approach K3s. Rank Picard is 1. You have very little geometry to play with. And so then we thought, well, maybe, OK, so here let me sketch the proof of a theorem for special K3s, elliptic K3s. So the statement is that the points are dense. And how did it work? Well, we have an elliptic K3, and we already know, or let's say we proved that we have infinitely many rational curves. Well, some of those curves will be multi-sections. Not all can sit in singular fibers. There are infinitely many curves. Well, rational curves do have infinitely many rational points, and they will intersect infinitely many fibers. And then these points in those fibers, maybe they are of infinite order in the fibers. And so this way you can generate more points. And it works. But you have to make sure that the rational curves that you're looking at are not, so to speak, torsion, that what they induce in the fibers are not torsion points. Well, this is some condition that needs to be checked. It's subtle, but it works. Dense after a finite extension of the ground field. So there is a finite extension of the rationals so that over that field the points are dense. Of course, yeah. So now, we didn't know what to do in rank Picard 1, but we thought, well, maybe we can look at 0 cycles of some degree. In other words, look at points in some extensions. We fix the degree of the extension, let's say quadratic extensions, other points dense there. Well, that means that we're looking at rational points on Hilbert schemes. So we have a theorem that if we have a polarized K3 of any degree, then you can, well, I don't know whether I wrote the correct n here. Yes, on some symmetric or some Hilbert scheme, rational points will be potentially dense. So for example, if you have a K3 of degree 2 times a square, then already on Hilb 2, rational points will be potentially dense. And so what's used here? Well, we use that idea of Yao-Zaslow that was then also developed by Bouville. We use this abelian fibration. I don't know how, well, we were aware of this paper, but so an abelian fibration is sort of an analog of an elliptic fibration. So what we need here, of course, we need multi-sections. Now, this time around, we don't find rational surfaces that could surface multi-sections, but there are nevertheless, surfaces with many rational points on them, potentially. And we can make these surfaces from, in fact, elliptic curves, genus 1 curves on the underlying K3 surface, and then propagate the points that we obtain in this way. But this is really all we had. And, well, so for many years, we were working sort of on other things, but so the big success of derived algebraic geometry, if you like, led us to think about applying some of the techniques, at least in the setup of K3 surfaces. All right, so there is this notion of derived equivalent K3 surfaces. And, well, there are many definitions. So one would be the orthogonal complement of Picard groups. The transcendental lattices are isomorphic as Hodge structures. Well, equivalently, there is some definition in this language, in the language of derived categories. There is some object in the bounded derived category of the product, so that the corresponding functor here is an equivalence of triangulated categories. So I want to say that it actually works over any field. You can write down the definition of derived equivalent K3s over any field, and there is a paper of Yao or Guiza and others where you can count the number of derived equivalent K3s, let's say rank Picard1. So let's look at some examples. You see, in high rank Picard, when the Picard lattice is big, the transcendental lattice is small because they have to fit into Z22, and therefore, in high rank Picard, derived equivalence tends to imply isomorphism, and so we don't actually get anything new. It's sort of the same. So, for example, if rank Picard is at least 12, or if the K3 has an elliptic fibration with a section, or if rank Picard is at least 3, and the discriminant of the Picard is cyclic. Now, so let me give you some examples here of, I think that's the lowest degree example of derived equivalent, but not isomorphic K3s. So we look at these lattices, two lattices, and we look at K3 surfaces where the Picard groups are these lattices. And split means over the ground field, right? There is no Galois action anymore on the lattice. This is what we have over the ground field. And so then the hope is maybe, there is some relation between arithmetic properties of these K3s. So let's try to explore that. So, well, first of all, both have 0 cycles of degree 1, both of these over any field. The first one actually always has rational points, again, over any field. And that happens because we have smooth rational curves on that surface, which intersect with, which have odd degree cycles. Intersect hyperpolarization in odd degree. And therefore, a rational curve with an odd degree cycle has to be a P1. So not only do we have points, we have actually 2 P1s full of points, infinitely many points on these P1s. Well, the other K3, in fact, has infinite automorphisms over some extension of the ground field, and so it has a potentially dense set of rational points. What we don't know, however, is that, first of all, the first one, which has infinitely many rational points, has potential density, that is, the risky density over some finite extension of the ground field. We don't know that. And we do not know that the second one, which has potential density, has actually points over the ground field, even though it has a 0 cycle of degree 1 over the ground field. So this is kind of a curious situation. And this would be sort of the first, maybe, test case of our hope that, well, maybe we can bootstrap some geometry and from one case to another case. So what I'm describing here is a joint work with Brendan Hassett from this year, and the paper is on my webpage. So, all right, so assume we have derived equivalent K3s over a field of characteristic not equal to 2. Well, then their Picard groups are actually stably isomorphic as Galois K-Bauer K modules. They're not isomorphic. I mean, I've just shown you two rank 2 Picard rooms, which are not isomorphic. But if you add Galois invariant sinks, they are. And the other thing of relevance in arithmetic geometry, Brouwer groups. So you may have heard of Browmanian abstractions, Brouwer groups. So Picard and Brouwer groups has invariants that play a role in arithmetic. So the Brouwer groups are the same in both cases. So, well, again, we can hope to relate the arithmetic. And then there is the result that if you have a zero cycle of degree 1 on one of the K3s, you also have a zero cycle of degree 1 on the other K3. And actually, it's more general. If you have zero cycle of any degree, then of this degree, then you'll have a zero cycle of that degree on the other side as well. So the index is preserved under derived equivalence, if you like. All right, so what do we know about finite fields? Well, there is a result from 2011 that if you have two derived equivalent K3s over a finite field, then they have the same number of points. In particular, if one has points, then the other has points. Now, what do we know over the real numbers? Well, if you have derived equivalent K3s over real numbers, then actually those manifolds are diffeomorphic, and in particular, one has points, the other has points. So the natural question is, what happens over the p-adics? And, well, finally, what happens over Q? So the hope is that over p-adics, you have the same property. Then the next hope is, well, therefore, the adelic points are sort of the same. The adelic points are the same. You could look at the Brouwer kernel, and the Brouwer groups are the same. The computation of local invariants, you can also relate them. Then the Brouwer kernels would be the same. And then there is a conjecture of Skorobogatov that, let's say, rational points are dense in the Brouwer kernel. In any event, you sometimes expect that the Brouwer kernel does capture a lot of arithmetic. So the hope, therefore, would be that over the rationals as well, if one has points over the rationals, the other has points over the rationals. But it's just a hope. It's not even a conjecture. So now, what about the p-adic case? So here is the theorems. Assume that we are looking at derived equivalent K3s over a p-adic field of residue characteristic 7, or for technical reasons, and assume that both admit ADE reduction, right? So we're now looking at mixed characteristic. Then if one has points, then the other has points. And now, just a comment. You see, having potentially good reduction turns out to be a derived invariant. So there is a recent paper by Matsumoto from 2014, literally months ago, where he looks at this property of derived equivalence. But, for example, we don't know whether or not having an ADE reduction is a derived invariant, even that, which would be a natural thing to suppose. Well, not knowing what to do with the p-adics for now, so let's focus on the geometric case. So we have a family of K3s over a disk. Well, we don't always have a section. We don't always have rational points over this field. So here is an example of a family without a section. So then you'd like to ask, does having a section, is this a derived invariant? If you have a derived equivalent K3, one has a section, should the other have a section?
Derived invariant of the family?
Yes, so K3 over a functional field. If you are derived over that field. So I will talk about what happens with derived equivalent, integrally. But now, so how do we think about this? Well, we know that after some finite base change, there is something called the Kulikov model. I don't know, Weierstrass models, a nice model of a K3 degeneration, which could be either a K3 surface or this, type 2. I like to think of this as a towel. You have rational surfaces at the ends, and then tick, 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 other surfaces in between. Or soccer ball, I guess, union of rational surfaces, combinatorial triangulation of a sphere. So there are these three cases, and they're well studied. And so here there is sort of a technical lemma. Assume that we have x and y derived equivalent over the field, and suppose x admits a Kulikov model without base change, right, over that field. Well, then y also admits a Kulikov model, and both sets are non-empty. So you're guaranteed to have sections, of course. Now, the non-trivial part is, well, there is this base change involved. You know, how do you get a Kulikov model to begin with? And so here, I just want to discuss one case of, one case that happens. So suppose we have some cyclic group that acts on a K3 surface via some quotient, another cyclic group, H, and that group is in the automorphisms of a K3, right? So then we can look at sort of an isotrivial family. You know, take a product on the first, on delta 2 with group G acts simply via nth roots of 1, and on here it acts via this subgroup of the automorphisms. And then we get sort of a twisted family, and we can look at what happens here. Well, as you can imagine, you can do this in the derived equivalent context, and you will see the group actions, here and there. And so here is a lemma that, well, we know when the quotient here, when this family has a section, it has a section if and only if the H action on x0 has a fixed point. All right. So now we have to analyze those fixed points. Now, the question then is, if you have, a K3 surface and some finite cyclic group acting on it, and another one, and suppose the action is compatible with an isomorphism of Hodge structures, does having a fixed point on x0, imply having a fixed point on y0, right? Completely down to earth. All right. So now what kind of cyclic automorphisms do we have on K3s? So the Euler function of that has to be less equal than 20. And it turns out that all such n arise. Now, and then you can look at those that preserve the two form, the symplectic ones. And in fact, the groups tend to be very small, so 1 lab to 8. I mean, you don't get very many symplectic ones, and a lot of the fun is coming from the non-symplectic actions and the mixture of those. So I thought that I should give you a table of all numbers with Euler function less than 20. As you can see, you can have quite interesting automorphisms, 66 and 50. And the way you should read this table is, well, if the automorphism is large, then those happen to be unique. The K3s carrying such large automorphisms happen to be unique. I mean, in high rank Picard as well. And there is an enormous literature, classifying, these particular K3s. And so in particular, 66, 50, 44, 33, all of these are essentially one K3. And so derived equivalence is not really that interesting for those. And then when the action is very, very small, symplectic, non-symplectic, it's sort of also well understood. You can analyze the fixed points. And so most of the fun is somewhere in the middle of this table. And then, again, a huge collection of papers and classifications and tables. You can have this fixed point locus and that fixed point locus. Some of the papers are recent: Artebani, Hume, Kondo, Mashida, Nikula, Noguza, Sarti, Taki. So many people looked at this, but there is no complete, no simple answer that you can take off the shelf. And therefore, this is still in progress, hopefully. Some combination of these papers, intersection, disjoint union, I don't know. Some combination, because there are actually some contradictions. There are papers that are inconsistent. Still, there is hope. So so here is a slide of things to do. Of course, we would like to have some mixed characteristic version of Kulikov models. I mean, it would be nice to know what happens if you work over the p-adics and you look at, the special fiber. What happens? How can you relate, with derived equivalent K3s? And naturally, Ludmila already brought it up. So there is this paper by Bridgeland Macchiosha that the Fourier-Mukai transform of K3 families over curves, it specializes. And again, it would be nice to have a mixed characteristic version of that for our applications. And it would also be important to explore what happens in the central fiber. I mean, they have just the results that says, it specializes, but what does it really mean for us? Well, maybe in sort of conclusion, so we know very little about rational points in general, rank Picard1 K3s, over non-closed fields, even over such fields as C double bracket T or the p-adics, and these are of course much more difficult, function field or finite fields of the rationals, and that we now hope that techniques perhaps in Fourier-Mukai transform derived algebraic geometry may shed some light on these arithmetic problems. Thank you.
Question?
It's about practical part when you apply algorithm. Yeah, actually, I've seen some new algorithm which is for any variety given equations in a number of variables, like this. You can calculate Euler factors in linear time in prime numbers.
Yes. Yes.
Is it?
So what's implemented here is essentially linear time for these K3s. And yeah, I mean, you can do in weighted projective spaces, hypersurfaces in weighted projective spaces. It's really practical, yes. I mean, it still involves large matrices. I think here it's 200 times 200 matrices that he's processing, but it's okay. I mean, many of them. So, well, if you have your favorite K3, we're happy to compute. I mean, I forgot to say that slide cost 120,000 hours of CPU time. Yeah. No. CPU time is free.
Other questions? If not, let's thank you again.